All right. Can you see this one?
Mm-hmm.
Okay. So we're going to talk about electrical principles today. Like I said, there's four groups. So it will kind of be very basic stuff. Um, Thanks to old Benjamin Franklin, we have a lot of things we're stuck with. He is the one that decided arbitrarily, because they didn't know any better, that current flowed from positive to negative. And we call that conventional current flow as opposed to electron flow, which is the opposite direction. Well, he had a 50-50 chance.
Yeah.
Um, we have kind of two kinds of current. There's direct current, which is like what you'd get from a battery or power
DC.
supply. A current always flows in the same direction, conventionally positive to negative. Uh, there's
The way
also
Christmas lights used to be, huh?
what?
Like Christmas lights used to be in the old days. One goes out, they all go out.
And then we have alternating current, which changes direction. It goes positive to negative and negative to positive. Um, and uh, RF, which is what we call it, is an alternating current. Things behave differently with alternating current than they do with direct current. And we'll talk about that a little more in a little bit. Benjamin Franklin did a bunch of things like capacitors and all kinds of stuff. So some of the terms, there's a thing called charge, and it's the total amount of elementary charges, and we measure those in coulombs, named after some old scientist. I think he was French, I'm not sure. Where an elementary charge is the amount of charge that's on an electron or a proton. They're equal and opposite. So in a typical atom, the charges on the electrons and protons, because there's equal numbers, cancel out. So an atom is neutral. However, if we provide enough energy, heat, or electric force, electric field, we can energize an electron that's in the outer shell to actually leave the atom. So we wind up with a electron which is negatively charged and an atom which is missing an electron, so it's now positively charged. And that's where we get the charge buildup, which causes the difference in potential and creates a voltage. And when we have that difference of potential, it can create current flow, which is really just the charges moving, being attracted, the negative to a positive and positive to a negative. And we call that current flow, and we measure it in coulombs per second, or amperes. So 1 ampere is 1 coulomb per second. And a coulomb is a whole bunch of these elementary charges. In fact, it's 6.24 times 10 to the 18th, which is a very, very large number. It's a billion. Where voltage we call electromotive force. That's why we use the symbol E. And we measure that in volts. And that is the amount of energy per unit of charge. uh, and it's equal to 1 joule per coulomb. Now, some of those things you don't need to remember for this exam. It's just trying to impress you with things that I know a little bit about. The main thing is to remember that charge is represented by Q, coulombs by a capital C, because we'll do capacitance as a small c later. Okay. We measure current, we use I, and we measure it in amps with an A for amperes. And we measure voltage or electromotive force, EMF. We use an E, and we measure in volts with a V for Volta, who developed the first battery. We'll use things like resistance, and we use an R to represent resistance, and we measure that in ohms, named after another little German guy who, by experimentation, developed what's called Ohm's law, where resistance is equal to the electromotive force divided by the current. That's a formula you need to remember. And we'll talk about that a little bit more. I mentioned direct current, which is current flowing in one direction only, conventionally positive to negative, whereas alternating is going to change polarity, positive to negative, negative to positive. Your household power is alternating current that's reversing direction 60 times a second. And we measure that frequency in hertz, which we'll get to, named after a guy named Hertz. So we use a capital HZ because it's a proper name abbreviation. We'll talk about conductors, which are materials which allow current flow. Typically, it's a metal, silver being the best, copper next, gold next, then aluminum, and then others like iron and stuff, which are not nearly as conductive. The one thing that metals have is they're atoms that only have 1 to 3 valence electrons. That's an electron in its outer shell. So they're very easy to energize and become a free electron. We'll talk about semiconductors, typically silicon and germanium. There's some high frequency stuff that's made out of gallium arsenide. They tend to be atoms that have a half full valence shell. And by themselves, they're not really a conductor, but if we add impurities, we can make them a positive or negative material and cause them to have controlled conduction. And then there's insulators, things like glass, ceramics, plastic, rubber, that oppose current flow. They tend to have a full outer valence shell. It takes a tremendous amount of energy to free an electron. And usually when that happens, you see some destructive consequences. That's just a little thing showing kind of the relationship between voltage, ohms, resistance, and amperes, where the volts are trying to force current flow, which is amperes, through that restriction, which is the amount of resistance in ohms. So the more resistance, the less current gets through.
Gotcha.
So we talked about voltage or as electromotive force or potential. There's a simple circuit diagram showing a battery connected to a resistor. And The I represents the current that's going to flow through that circuit. And it will be dependent upon the value of the voltage of the battery and the resistance of that resistor in ohms. And that little horseshoe is a Greek letter for omega, which we use a lot to represent ohms because it sounds like an ohm. Another water analogy where we have water pressure, but we have a high resistance, so there's no current flow. If we open that valve and allow current to flow, we now have current, which is essentially, a very high resistance or a very low resistance. So the potential difference, which is due to the amount of charge, the difference in charge between positive and negative charges, which creates an electric field. And that electric field is what generates the force or energy to energize those electrons and make them what we call free electrons. Mm-hmm. And that's a key thing, is a free electron, which is what allows current to flow. You have to have electrons that are free to move and recombine maybe with another atom. As those electrons that are energized and free recombine, they give up that extra energy, and we call those phonons. And it depends. The frequency of it will depend on the amount of energy. So it can be anywhere from lower infrared up to visible light and X-rays, because light is also an electromagnetic wave, just like radio waves, just different frequencies. Mm-hmm. This is a typical copper atom. It's called the Bohr model, where we have these shells. I don't think anybody knows what really goes on. And it has one electron in its outer shell. And that electron is very easy to energize and escape from the atom and become a free electron. This is kind of showing in metals, it turns out that under normal circumstances, there's enough heat, you wind up with free electrons without even having to have an electric field. So there's always some free electrons in a metal, which I think explains one of the reasons why metals feel a little bit different, because of those electrons moving around. When you get to a semiconductor, the energy required to make that a free electron has to jump this band gap, which is the amount of energy it takes to go from the red to the blue. And when we talk about semiconductors next week, we'll talk a little bit more about that band gap, and it's different for different materials like germanium and silicon. In the case of insulators, you can see that band gap is very big, which is why they don't conduct unless you provide enough energy for them to like arc over or something. If you've driven down the road and see the power lines and sometimes you hear them crackling, that's because there's enough energy there that you're, usually because of salt, but you're getting electrons to jump that gap. So, first question. What's the electrical term for the force that causes electron flow?
Voltage.
What happened?
Very good.
Weird. I lost my, can't see anything now.
I didn't hear that.
I can't see anything right now. It's weird.
I can though.
Yeah. Let's see if I can get this. Okay, there it is. All right. The picture just like lost it. Okay.
Okay. Current, which I mentioned, is the flow of electrons or charges in a circuit. And we use the letter I to stand for current. Conventionally, it flows positive, negative. We measure it in amperes, and we use A to stand for an ampere. Like I said, an ampere is equal to 1 coulomb per second. The same little circuit here showing the battery and a resistor and the current. Some more water analogy, which kind of is the same thing.
What? Oh my goodness. Wait.
What?
So here's a picture of voltage on the left. And amperage has 2 tanks.
Well,
Just
you notice
show
the
me
pipe.
different flows.
The pipe is different size.
Okay.
Okay. So the skinnier
you.
one has more resistance
Very unobservant of me. I see it now. Yes, thank you.
and has less current flow.
I got it. I'm with you now.
Okay. Water behaves pretty much the same way as basic electricity, as long as we're talking about direct current.
That's what my brother said when he was 14 years old.
So what's the name for the flow of electrons in an electric circuit?
Current.
Yeah.
All right.
Current.
Electrical current is measured in which of the following units?
Amperes.
Right. A French scientist.
Oh.
Volts.
Ohms?
No,
Hmm.
ampere.
Amperes. That's right.
I thought you were saying it was wrong. Sorry.
I forgot his first name, but it's just another old dead
French
French guy.
Scientist. Oh, wow.
So now resistance, because we've talked about voltage and current. Resistance opposes the flow of all types of current, AC or DC. It doesn't care. We'll talk about capacitors, inductors later, and they behave differently whether or not it's DC current or alternating current, or RF, which is really alternating current. Nothing really special about it. So we measure resistance in ohms. Sometimes we use that little Greek omega signal, and we use R as to represent resistance. So it's our same little circuit you've seen at least 3 times now. And yet another water analogy. So what are the units of electrical resistance?
Ohms.
Ohms.
Ohms. There used to be a thing called Mohs, which if you notice is, well, not exactly.
MOHS.
Yeah. Yeah, spelled backwards. We used to use that for conductance, which is the reciprocal of resistance, but they replaced it with Siemens. I don't really know why or exactly what this guy Siemens did, but apparently it was enough to get his name used. So what type of current flow is opposed by resistance?
All of them.
All of them. Right.
All above.
Right. Resistance, pure resistance doesn't care. When we talk about other stuff, we call it reactance because it's frequency dependent. Let's see. Really, there's nothing new on this one. We've already talked about batteries supplying direct current. Power supplies do. And alternating current is what you have in your house. United States, it's typically 120 volts AC at 60 hertz. We used to call it 60 cycles, but they decided to use hertz. And remember, it always alternates between positive and negative directions.
Mm-hmm. It was 220 in Europe.
Yes. And they have different plugs.
Yeah, boy, do they ever. The UK has different plugs than the rest of Europe. They should all be on one.
Yep. Yeah. And I'm not sure, but I believe they're 50 hertz, not
50?
60.
Wow.
So in a lot of cases, you can't just plug something in with an adapter plug because of the frequency. This is this little chart. It will help later on, but it shows how a sine wave, which we'll talk about a lot, is actually constructed from rotating a radian or radial around the circle. So if you look at that red
Arrow.
we call that a radian.
Okay.
As we rotate that counterclockwise, each one of those steps, and we plot the height of it, you'll get this sine wave.
Mm-hmm.
Kind of like what you see if you watch somebody going by on a bicycle and you watch their foot go up and down. Same kind of thing. So that's how a sine wave is generated. And those will show the different phases of that cycle, which we'll talk about later, just kind of giving you a preview of some of the stuff. You don't have to remember that formula for the sine of omega t.
Yeah,
plus,
that looks like trig.
Mm-hmm.
Yeah, it is. And we will do a little bit of
calculus too, but trig definitely. Wow.
So which of the following describes alternating current?
Let's see.
See.
Oh, also, just to get you used to it, on the answers, try to use the phonetic alphabet because we use it in radio. So it would be Alpha, Bravo, Charlie, and Delta.
So use the military.
No.
Yeah, military would be Baker, right?
Baker for Bravo.
Okay.
Military is Bravo.
Oh, okay.
So which one would you use, Baker or Bravo?
Oh,
military is Bravo.
We normally use Bravo.
Because you got Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, Golf,
Hotel.
Indigo for I.
We use India.
Oh, India?
Mm-hmm.
Wow.
Juliet.
Oh, yeah.
Kilo. Lima.
I forgot M. I know
Mike.
November. Oh, Mike.
M is Mike.
Oh my gosh. Yeah, and then November.
November.
Oscar.
Oscar.
Papa. Let's see. DQ.
Papa.
Quebec.
Quebec.
Let's see,
Romeo.
Romeo. S. Sierra.
Sierra.
Tango. Uniform. V.
Uniform Tango.
Yeah, Uniform Tango. Or Tango Uniform. I forget V. Victor. W. Whiskey. X-ray.
Whiskey.
Yankee. And Zulu.
Zulu. Right. Yeah, we do call signs phonetically usually on the net. I'm Whiskey 3 Romeo Delta Lima.
Gotcha. Oh, I saw that. Right? Yeah, it looks like Wordle.
Yeah. I had somebody ask me.
Do you play Wordle?
Okay. What's the answer?
C, Charlie.
Yes, C. C.
Okay. Frequency. When we talk about alternating current, we need to know how many times per second it alternates. And we measure that in hertz. So 1 hertz is
1 cycle?
1 cycle per second. So 2 hertz would be 2 cycles per second. I still like cycles per second.
Yeah, is that one like, you know, how I was breaking up at the beginning, the video, would that be something like that, where if you're not on the right frequency, you'd see something like that? Or hear something like that, you get staticky or break up?
Well, if you're not on the right frequency, yeah, you definitely get some, like on voice, you definitely get odd sounds.
Okay.
Particularly single sideband.
Mm-hmm.
FM, not so much, but AM and single sideband, yes.
Yeah.
So the frequency we measure in hertz, and the period, which is how long it takes to complete a cycle, we call the period, and that's 1 divided by the frequency. It gives you the time it takes for 1 cycle, or however many cycles you got.
Gotcha.
So what describes the number of times per second an alternating current makes a complete cycle?
I'd have to say delta.
Frequency. Yeah.
Yeah, see, these are all easy, right?
Mm-hmm.
What is the unit of frequency?
Alpha.
Hertz.
Alpha.
Isn't that car company?
Alpha. Oh, sorry, alpha.
Now, this is Heinrich. Okay, so now we'll talk about conductors a little more. And like I said, the main thing to remember that metals have many free electrons.
Mm-hmm.
Even at like room temperature, you see on the left, you've got little electrons floating around, not going anywhere in particular. Over on the right, when we apply a voltage or a force, it's going to cause those electrons to move in one direction, and the positive charge, or which is kind of hard to explain, but because when an electron leaves the atom becomes a positive ion.
Mm-hmm.
And you can see apparent movement of those positive ions, even though the atom doesn't necessarily move, because of the electrons moving and recombining. So when you apply that voltage, creating that electric field and the force, that creates current flow, which is those electrons moving. Again, the copper atom, which we talked about. And then I probably need to take these out because they're redundant. So when we talked about conductors, metals are the best conductors because they have a very low resistance. Silver being the best. Copper is almost as good. It's a lot cheaper than silver. At least it used to be.
Mm-hmm. Yeah.
Gold is not quite as good, and it's a lot more expensive.
Mm-hmm.
It was up $3,500 an ounce yesterday.
Woo.
So basically, for most electronic stuff, we use copper.
Mm-hmm.
You'll find gold a little bit where you use it on connectors and things because it doesn't tarnish.
Yeah, okay.
Where copper oxidizes easily, and so does silver.
Oh, yeah.
So why are metals generally good conductors of electricity?
Bravo.
Mm-hmm. Bravo.
Bravo.
I'm a slow reader.
That's all right. You need to read the question slowly. There's no time limit on the exam.
Oh, good. That was one of my
Well,
questions.
I mean, within reason.
It's not gonna, yeah, within reason. Yeah, I got you.
After 12 hours, I'm sure.
Oh, no, I'm not gonna take that long. Heck no.
Typically, it's about 20 minutes.
Okay.
Insulators, which we talked about, are the non-metals, which basically do not conduct. So plastic and glass are the most commonly used. If you look at, your power lines along the road and you see those little disc things all stacked up,
Mm-hmm.
typically those are actually made out of glass.
Even now.
Yeah.
Wow.
I mean, glasses.
Mm-hmm.
We haven't come up with many new insulators. Glass is cheap.
Yeah. Burn some sand.
This again is kind of showing where conductors only have a couple valence electrons and insulators are almost full shell. We got somebody new. Oh yeah.
Come on in. Micah. Oh. Bravo.
Bravo.
Let's see if Laura, can you hear us?
I can. I'm in the car.
Oh, okay.
How are you?
We started.
We were at the gym. We had a previous engagement.
Okay.
Is it okay if I keep my video off?
It's
now?
up to you.
Yeah, that's cool for me.
Okay.
Yeah.
It's less
Are we doing-
distracting for me, so that's good.
Okay. So we said bravo, right?
Yes.
Oh, I get it.
Okay. So we talked about current being measured in amperes. That direct current flows in one direction and alternating changes direction per cycle.
Mhm.
Electromotive force we measure in volts, and that's what creates current flow.
Mhm.
We measure frequency in hertz.
Mm-hmm.
We measure resistance in ohms.
Mhm.
And resistance is the opposition to current flow, regardless of whether it's DC or AC. Conductors have many free electrons, and insulators basically have no free electrons.
Mhm.
Okay.